Okay, let's get started. We're on to chapter 2. So by now we could probably assume that matrices are important, as we've gone through one major application of matrices with the systems of linear equations, and then we talked about its relationships with vectors, and then there are a bunch of other applications that we didn't really dive into too much, but in general we can say they're pretty important. So the second chapter is devoted to just working with matrices themselves, and then every once in a while reaching out for an application and putting it onto this. But I think matrices themselves are a basis or foundation for studying these things, these elements. So we can think about them as vectors, as vectors where they're beyond just scalars or real numbers or complex numbers for that matter. They're beyond just those entities. They actually contain a lot more information than these scalars. So we know that vectors contain information that can be listed in a one-dimensional array. Matrices would contain information that can be listed in a two-dimensional array, and that's where we're at. So we're going to study some of the basic matrix operations in this first section, and then continue on with some more important properties of matrices throughout the rest of the chapter. But first we have to kind of get used to some of the language and some of the notation and some of the basic vocabulary, I guess. So an m by m matrix, m by n matrix, has m rows and n columns. We've already talked about that. And they contain entries that are scalars. And by scalar, for our class, we just mean real number. In other classes, they can extend to complex numbers. But for us, we'll just deal with real numbers. And then the ith row and the jth column would be something that we can identify. And we would call that A sub ij. And whenever we denote something with some number, the indices here, the subscripts, would be the index in the row first and the column second. So the I is denoting on a particular row that we're in. The J is denoting the particular column. Yeah.
So I could be like the second row.
Yeah.
So then it's not like a specific placement.
Right. So they use I and J for indices, and then they say it's generic. So when you say A1, 2, so you have to look at your matrix. These are stars that don't look like stars anymore. And so first row and second column. So this is what we're referring to. Okay. So they say I and J to make it generic, but then when we want it generic, we'll say ij, A sub ij. And then when we want something specific, when we're working with a problem, then we'll actually point out the row and column. I'm sure there are, but they don't work with that with math. For 3 dimensions, they tend to just layer it around. So you have a 2 by 2 matrix. Say you want to express something, which sometimes you might. You want to express something in 2 by 2 by 3, for example, then you just kind of spread the 3 matrices around, and then maybe leave the 4th quadrant blank or something. Like a good example of that would be like RGB in a picture. So the picture, each pixel in the picture would be the strength of the color, right? And so the picture is 2-dimensional. So you say you had a 100 by 100 pixel picture, and then each pixel would have an R, a B, and a G. So that would take your 2-dimensional picture and have 3 different matrices representing that, one for the red, one for the intensity of the red, one for the intensity of the green, and one for the intensity with the blue. Did I do that in order? Red, green, yeah, RGB. So you kind of layer it. So that, ideally, we would want to work with a 3-dimensional matrix with that, but we don't have, people thought maybe 2-dimensional matrices were enough, so that we would just have 3 different 2-dimensional matrices to deal with.
Yeah.
And generally you do the operations on one matrix, they're the same operations that you'll do to the other matrices. So like if you want to blur out a portion of the matrix, whatever you do with R, you'll do with G, and then you'll do with B, and then it's the same thing.
Keep all 3 the same.
Yeah. All right. So here is our basic language for the matrices. And we're going to keep referring back to the columns of the matrices. As vectors. So each column of A is a list of m real numbers, because there's m rows. So a column would be a vector with m, that's the number of rows, with m rows. And then we'll write it like we've done before with each of these vectors. They're bold and they're not italicized here, so I am trying to make a big deal that these are vectors. And then the number ij, so if A sub ij, you would look at the column that they're in. They're in the jth column. And then you look at how far down in the row are you going. You're going the ith entry down, right? So back to this picture over here, A sub 1, 2 is going to be in the second column. And then it's going to be the first entry. The first entry in the second column. Yeah? Oh, yeah. So you just have to write it carefully. So A2312. So you just have to write it carefully. So, yeah, commas are sometimes useful. I think that's what some people do. Yeah. Yeah, come think about it. I think commas are appropriate for this, especially when you get to double digits. Hopefully, we don't get to do, we don't have to do any double digit matrices, because then that would be big. But when you're programming stuff on the computer, these things are just going to be the subscripts of your arrays and stuff. All right. So that's just notation, a similar notation from last time with the column vectors, and then we're just looking at each individual matrix element now, or each individual entry in the matrix has a specific index value that we can, index values, there's two of them, that we can call on. All right, so we have a handful more definitions. The diagonal entry would be the entries that would have the same column and row. It should be AII, I think. Oh, this is sometimes how they write the matrices. A is equal to, and then the square brackets Aij, that'll represent the whole matrix. And then the diagonals are the ones that have the same column and row subscript. And even if it's not a square matrix, we can still refer to the diagonal, right? Because that's something that we're going to refer to. Usually we think of diagonal if we have a perfectly square matrix. But if your matrix is not square, you can still refer to the diagonals. If they're talking about the same row column, that just means there's these other things that we won't consider. And so when we do the row echelon reduction business, we try to make the diagonals to be 1. Of course, sometimes you have free variables and they scoot over, but then these are the numbers that we want to focus on. A diagonal matrix, so this is a specific definition now. A diagonal matrix is a matrix that would be numbers in the diagonal. Some may be 0, but there is going to be some non-zero things in the diagonal. And then if there's 0 everywhere else, and here we'll denote it with just zeros in the space that would include everything that's not in the diagonal, then we call that a diagonal matrix. And something like this can be written essentially as a vector, right? Because it's just same row and same column. So
Okay, well, if everything else is 0, how are not all those 1s?
they could be 5, 7, 3, 0.
They'll be the same number?
No, they don't have to be the same number.
Okay, so this is
So as long as it's as long as there exists some non-zero values in the diagonal, then we call this a diagonal matrix. More importantly, as long as it's zeros everywhere else. We'll call it a diagonal matrix. Okay? And it turns out that doing the matrix algebra on diagonal matrices are going to be really easy for us because, like I said, the only information that you have is in the diagonal, which can be written as a vector, and we can easily deal with vectors.
So then if they all are 1s or 0,
Well, those two are different. If they all are 1s, then what's it called? Then, yeah. So if they're all 1s and zeros everywhere else, then it's the identity matrix.
It is a diagonal.
It is, the identity matrix is a diagonal matrix, but it's a special case because all the entries are 1.
so when we reduce row echelon form that diagonal,
This one?
the one on the red on the left,
Oh, then that's not, officially this is not a reduced row echelon form because for the reduced you have to make everything into 1s. Right?
and then we have a 0, so we can't ever get there.
Well, in this case, you can reduce it to just, it'll be 1, 1, 0, 1, 1. It would be a reduced row echelon form. It would be a diagonal matrix, but it won't be the identity because there's a 0 in there.
And then we could shorthand it by doing 1, 1, 0,
110 and 1, yeah, because that's all the important information. In fact, when you're programming, when you're doing stuff with a computer and you're doing some programming and you need to express these matrices and you know that you're going to have a diagonal, you don't need to have a 2 by 2 array. You can just have a vector or a one-dimensional array to represent your matrix. And then if everything's 0, then that's called a 0 matrix. Now, like the 0 vector, it is important to denote that it is a matrix and not just a scalar 0. And I think in the book they just say 0. It's fine to write zeros. But I think I've also made a point that when we're dealing with a 0 vector, I always want you to put the arrow on top to say it's an actual vector. When we're dealing with a 0 matrix, I prefer if you actually put square brackets around it to say that it's a 0 matrix and not just the number 0. And so let's try to make that distinction. It's not that big of a deal, but it's a good convention to use so that you know the difference between the number 0 and the 0 matrix. Okay, any questions? All right.
You said it again, so you'll write the 0 matrix as 0 bracket?
Yeah, 0 with the square brackets around it. Just for our class convention. You know, out in the real world or out in, you're doing computing work or you're doing some matrices in other classes. Sometimes they don't care if you write the brackets or not. But just for our sake, it's good to remember. Okay. What else do we got? Equality of matrices. Now this is kind of silly, but there's a lot of silly things that need to be said. So 2 matrices are equal if they have the same size and all their entries are equal. And so sometimes we might say matrix A is equal to matrix B if and only if all the elements A, I, J, all the entries in matrix A will match with the entries in matrix B. Will be equal. Like I said, it's painfully obvious, but it needs to be said. Well, you can't mix up the rows or columns. It just has to be the same. Exactly. Yeah. Exactly the same. No, because if it's a multiple, then that's called something else. There's a scalar multiple of a matrix that we're going to define, kind of like the scalar multiple of a vector, but here it's exactly the same. Okay? So we're kind of starting from scratch. We're like, back in grade school or whenever, kindergarten, is when you start first learning about your numbers, and then you start adding them and multiplying them. So we kind of had that. It wasn't much in this class, but more in Calc 3, I remember, there's some growing pains when we're starting to learn about vectors also. We define vectors, and then we have to define how to add and subtract them. And then we have the scalar multiplication, and then we have this dot product and cross product and all that stuff. So the same thing. We have matrices. We have to define the matrix. We have to say when the matrices are equal to each other. And then we'll talk about adding, subtracting, and then multiplying. It's going to be kind of our highlight today. All right, so the 2 matrices are equal if all their elements are equal. They also have to be the same size. Of course, if you have a 2 by 3 matrix and a 3 by 2 matrix, those are not going to be equal to each other, regardless of how they might look like. So they have to be the same. So addition and scalar multiplication, kind of like the same with vectors. And when you scalar multiply by a negative, then kind of subtraction kind of gets built in as well. So to add two matrices, you do component-wise addition. And to scalar multiply, you scale every element in the matrix. So let's do some really simple examples. 1, 2, 3, 4. Oh, by the way, for you to be able to do addition, the matrices have to be the same size. Otherwise, it's not going to work. And there's no special features to make it work unless you cheat and add more rows or columns to one or the other matrix, and then it doesn't really fly very well. So the addition of matrices is you simply add the components. 6, 8, hope I'm doing this correctly, 12. Okay, did I do that right? 1 plus 5, and then 2 plus 6, 3 plus 7, and 4 plus 8. Always worried with a little math. In the scalar multiply, you multiply everything. So there'd be 7, 14, 21, and uh-oh. 7 times, oh, 28. That's not, I thought I was squaring it. I thought I was raising the power. Okay. So with that special notation that we have, we could say A plus B is equal to adding all the elements Aij plus Bij is going to be adding Aij plus Bij to go in the Ij element. So it's a term-wise addition, just like vectors. And then same with the scalar multiplication. R times vector, or R times a matrix, is going to be R times Aij. And all you're doing is for every single one, you're multiplying every single element. Now, it's important that this scalar multiplication there's an important distinction between that and what we're doing here, and there's going to be an elementary row operation where we multiply one row by something, and we only multiply that one row. And so that's going to be important that we know the difference between that particular elementary row operation versus this scalar multiplication. And the scalar multiplication is every element. Okay.
Why do we have the Ij outside the bracket down there?
Oh, because I guess I wanted to make this the ijth element. I want to make sure that this is clearly the ijth element. I should probably put that here also. I'm making that the ijth element of that new matrix that has been added, or the new matrix that has been scalar multiplied. All right. Got addition and scalar multiplication. Again, very similar to the vectors that we've studied. There's no geometry here, though. Geometry for vectors, you know, the parallelogram and the diagonals and stuff. The subtraction will work the same way. When we subtract, it's like adding two things, and then the second one was scalar multiplied by -1. But that's just a subtraction. Yeah.
So in this addition, we end up with one answer.
Yeah, it'll just be one matrix. Uh-huh.
The IJ, or just one of the entries.
No, by this, I mean the whole matrix. So when you add two matrices, your new answer is going to be a matrix of the same size.
It's just in my assumption of the notation. I thought that you have AIJ and you're talking about one number.
Yeah, so there's A11 plus B11, but that's only this first slot right here.
Okay. Yeah.
And then now I want to do that for every single one of the I's and J's. So I have to do that with A12, and then I want to do that with A21, added B21, and then A22. That's why I have the IJ on the outside also.
Yes, yeah, I just made a bad assumption. I figured you were talking IJ, you're talking specifically some numbers, but you haven't picked them out yet. But they are placeholders for all the possible numbers.
Yeah. Yeah, I think by putting this IJ on the outside, I mean to do that for every single entry of the
Yeah,
matrix.
no, I just didn't realize that's what the
Yeah.
IJ meant.
Yeah.
Okay.
Okay. So we got addition, scalar multiplication, and I think we should be ready for the multiplication, although they put off the multiplication till later. All right, here, we have some properties. Some properties of the addition and scalar multiplication that they put together as a theorem. So that's worth looking at. And it kind of seems like it works just like the real numbers that we had, or more importantly, it works like the vectors that we've seen before. And we can identify a couple of these things as something that we've seen that have been pretty popular, or pretty, what do you call it? Pretty common. We can say that addition of matrices is commutative, which means we can switch the order and we'll get the same answer. We can say that the addition of matrices is associative. Which means if you have three of them, you can group them 2 by 2 or 2 at a time, and it doesn't matter how you regroup them. It'll be, it'll still work out. And the third one says that 0 is the additive identity. And then the next two are, this should be S, sorry. SA. The next two are forms of distributive properties. And the distributive property works with when you're adding two matrices, or distributive property works when you're adding two scalars. So the distributive property has an addition and a multiplication involved, and here we're dealing with the scalar multiplication. And so the distributive property works in whichever one you're distributing. And the last one is another form of associative property where you can regroup your scalars. You can collect your scalars. Although I don't know if it's actually called associative in this case, but but it kind of looks like the associative property for addition, except this would be an associative property for scalar multiplication. Vectors work the same way. All these properties, if you change a matrix A and B to vectors U and V, you'd see the same properties for vectors. Okay? So it might be worth proving some of these things, and you can look at the textbook for proofs of some of these. They tend to, when you have a multiple property theorem like this, they just usually prove one or two, and then they say the rest is for you to figure out. Now let's see if we can prove one. Let's prove this last one and see if we can prove it. As a math major, you're going to be doing a lot of proofs. Maybe theoretical physics too. So to prove this, we have RSA, and then we could try to use some shortcuts and say R times S, and then we'll start using the IJ notation. And this is R S A times IJ. So each of the elements now are S times the element or the entry, and then we can multiply the whole thing by R inside. And then we can gather the RS out. And then we can take that out of the matrix, and then it's one of those things that seems really obvious, but the proof is kind of has to be explicitly spelled out. So what you're saying is you're going to multiply the S first, and then after you multiply the S, you multiply the R, and then each of those elements are now going to have a factor of S and R that you can take out, and then you can take that out of the matrix, and then that's what you have at the end. Okay? All right, let's move on now. So we got addition and scalar multiplication. The next thing is the matrix multiplication. So let's take a look at matrix multiplication. Now the definition of matrix multiplication is kind of weird, and this is not the way I've normally defined matrix multiplication in the past. But the book really likes the idea of working with column vectors. So it says here, when a matrix B multiplies a vector X, it transforms X to B of X. So we're going to try to look back in last chapter, the end of last chapter, when we're doing transformations. And what we're saying here is that they have this graphics where they have X, and that gets sent to B of X by the transformation B. So we can think about this as domain, and then your output would be your range. And then, so this is another vector, right? This is a new vector. And that vector can get sent to another vector if we have another transformation called A. Then we're going to apply A to B of x. So the idea is to go from vector x to this new vector in one shot, and this is that multiplication vector A times B applied to the vector x. So that's what they're trying to go for. That's how they're defining the matrix multiplication. They're defining the matrix multiplication as a composition of matrix A and matrix B to get to your output. And so the definition here breaks up your matrix B into the column vectors so now these are vectors themselves, and then you're going to apply the transformation A to each of these vectors. Okay? So that's really not the best way to define multiplication. We'll find another way to define multiplication. But for now, let's think about this idea of a transformation. So let's do an example. And let's say we want a transformation that goes from R2 to R2. Let's do a B transformation first, from R2 to R2. And we're kind of familiar with some transformations from R2 to R2, right? Let's say B stretches your vector by 3 units. Okay? And let's say there's another transformation A going from R2 to R2. Oh, this should be R2 to R2. And then what does A do? Let's say A rotates the vector clockwise by 45 degrees. So rotates the vector clockwise by 45 degrees. So if we combine these two transformations, it should result in some sort of scalar multiplication, or vector, or matrix, matrix multiplication, right? So let's try to figure out what each of these matrices are. So B, if you have B, and we'll take our basis vectors, E1. If we're going to stretch this by 3 units, what's this going to equal to? 3, 0, right? It's really just multiplying the vector by 3. We're extending it by 3. And then it's going to act on E2, which is 0, 1, the same way. So we're going to multiply E2 by 3, and that's going to be 0, 3. Right? So this will actually give us our matrix. Remember? If you know what it does on E1 and E2, then you know what it does to everything, and you can use that matrix. And these just turn out to be the column vectors of your matrix. And so A is a rotation 45 degrees in a clockwise direction. So if you imagine your vector 0, 1 that rotates 45 degrees clockwise, where are you going to end up? So that's the same thing as root 2 over 2, yeah? So that's the x stays positive and the y goes down negative, right? And then we do the same thing to figure out what happens to your E2 vector, and that's the vector that was up here, and a rotation in a clockwise direction would put you in the first quadrant, in the middle of the first quadrant, and then that would be a positive for both. Okay? So I have a matrix A now. So I could take a vector in the domain space and then use B to bring it to another place over here. So what that's going to do is going to stretch your vectors out first. After you stretch your vector, that's B, and then we're going to do the rotation. So we rotate it using this matrix. So according to the definition of according to this definition, AB is going to be your matrix A that's going to get applied to your, well, that's not your matrix A. Your matrix A is this big mess. Yeah, we can bring out the 1 over radical 2. We'll do that in the next step. And then you have to consider these things as vectors. So the vectors that we're dealing with is all the column vectors of B, which is just 3, 0, and 0, 3. According to this definition, let's do that. Let's bring the vectors out, the constants, 1 over root 2. So this will be 1, 1, negative 1, 1. I think that's easier to deal with. And then we're going to apply that to vector 3, 0, the first row. So what we're going to do is we're going to get a column vector out of this. And then we're going to get another column vector when we take our matrix A and then we apply it to the second column, 0, 3. This is another column vector that we're going to get. So the idea is that with this matrix multiplication, the idea is that we know how to apply a matrix to a vector, or a vector to a matrix. We know how to do this. So we got the row and the column to multiply or to dot, so that's 1 times 3 and 0 times 1. 1 times 3 plus 0 times 1. That's going to be one number in the first entry, and then this vector will be negative 1 times 3, 0 times 1. And then we'll do the same thing for this. I'll just put the answer 3 and then 3. So then we get 3 times 1 over root 2, 3 times 1 over root 2, negative 3 times 1 over root 2, and 1 over root 2 times 3. So this is your product of two matrices. That involves stretching your vectors and rotating your vectors. Does this look familiar? Yeah.
Same thing as saying like the transformation is increasing by 3 and then rotating.
Yeah. Yeah. It's increasing, it's making your vectors 3 times the size and then rotating it. Yeah, this is the last problem on the test. You didn't need to use matrix multiplication, you just kind of figured out what to do with the things. All right, any questions? Let's do another one. So before we do another one, let's see if we can find a more streamlined way of doing this, because breaking up the second matrix into a vector and then doing this vector onto a matrix is not really the best way to do this. So this is your final answer. This is a good answer, but let's see if we can find another way to do this matrix multiplication. So let's rewrite AB equals 1 over root 2, 1 over root 2, negative 1 over root 2, and positive 1 over root 2. That's A. Matrix B is 3, 0, 0, 3. And so what we're going to do is we're going to go through this we're going to redefine the way that most people do matrix multiplication. And the way most people do matrix multiplication is that you need to fill in the slots here. And to fill in the slots, you take the rows of the first matrix and the columns of the second matrix, and then you're going to put it together. You're going to do a dot product, essentially, an inner product of those vectors. And then this is in the first row and the first column, so you're going to look at row 1. So on the 1, 1 position, this is 1 and 1, not 11, right? So in the 1, 1 position, it's going to be the computation of the dot product between the first row and the first column. So this is 1 over root 2 times 3 plus 1 over root 2 times 0. So that's the first slot. To get to the next position, you're going to take the first row again, but this time you're going to take the second column. So first row, row 1, and then column 2. So row 1 and column 2, that's the 1, 2 position. And in the 1, 2 position, you're going to do that dot product thing again. So the dot product is going to be 1 over root 2 times 0. That's the first element. And then 1 over root 2 times 3. So that's going to be in the 1, 2 position. And then we go to the second row. The first row is done, and we've distributed it to the first column. Now we go to the second row and the first column. So we're looking at row 2 now. Row 2, column 1. So the 2, 1 position is going to get the dot product of row 2, so that's negative 1 over root 2 times 3 plus 1 over root 2 times 0. And then finally, the second row and the second column, negative 1 over root 2 times 0 plus 1 over root 2 times 3. And this is the second row, second column position. Yeah.
Wait, the second one's positive, right?
This one,
No, the second one, 1/2. 20 over root 2.
this one is the only negative. Everything else is positive.
Oh, okay. Because I thought there was a negative one.
No, there's only this one negative, and that only happens in the second row and first column, because the second row and second column, that gets dotted and becomes 0. So that disappears. Oh yeah, so this is negative, but it disappears because it's multiplied by 0.
Wait, it should be positive, right? Because we already had a negative in the first one.
Well, this is under my second row and second column computation. I have a negative 1 over root 2 times 0. So that's negative 1 over root 2 times 0. Second row and second column. So this number over here is negative. That was negative from our A that we got. But you're going to multiply it by 0, so it disappears anyways. So anyways, if you simplify that, you're going to get the same thing that we got earlier. Okay. Now let's take a look at these two transformations again. And when we do the when we extend the vector by 3 units and then rotate it, is that the same thing as if when we rotate it first and then extend it by 3 units?
Yeah.
It's the same thing. So it looks like we can switch the order for this transformation, right? It turns out that multiplication of matrices is not commutative, not necessarily. Some can commute, but some may not be the same. So can you think of an example of a transformation that we've done from R2 to R2 where if you do one thing first and then the second, it might not be the same as if you do the second thing first and then the first? You understand what I'm asking?
Yeah.
Yeah, when you project it, it goes down, right? So when you project it, it goes down. You lose a lot of information when you project it. So let's think about an example. If we rotate it like 45 degrees and we rotate it 90 degrees and you project it onto something, then it would be different if you projected onto something and then you rotated it. Okay, so I want you to think about that, and maybe I'll actually write up that example when we come to the commutative property or the non-commutative property of matrices. So we took two 2x2 matrices and we used their definition, and then we redid the same 2x2 matrix and used a quicker way of doing the multiplication. And so let's do another example where we have to multiply a couple of matrices. And the example that we had was a 2x2 matrix, and And it turned out to be commutative, that we could switch to order and we'd still get the same answer. But in general, that's not the case. And here's another example that they have in the notes that I'd like to use, where you have a 2 by 2 matrix. And what's the second matrix? A what by what? Row first, right? So it's 2 rows and 3 columns. So this is a 2 by 3 matrix. So let's try to compute AB, the product AB. And let's see what we get. This is an example of matrix multiplication. Another example.
But we're not talking about the multiplication where
Okay.
b is not equal to times a.
Well, we'll see. We'll see what happens. We're going to compute AB in here in this case, and then BA, and we'll see.
Okay.
So if we follow that pattern of doing the matrix multiplication, here's what we could do. We remember the first matrix, we're always looking at the rows of that matrix, and we're going to match it up with the columns of the other matrix, right? So in my first entry, I'm going to have a 2, 3 dotted with 4, 1. So 2 times 4, 8. And then 3 times 1 is 3, and that's 11. Is that right? Okay. So 8 plus 3 is 11. That's my first component. And then let's do another one. I'm going to run out of highlighter color here. So the first row, the second column, first row, second column, that would be on my 1, 2 slot. In my 1, 2 slot. And I have 2 times 3 is 6. 3 times negative 2 is negative 6. And you add that, you get 6 minus 6 is 0. And then let's do the first row and the third column. So that's the 1, 3 spot in my new matrix product here. 2 times 6 is 12. 12, 3 times 3 is 9. 12 plus 9 is 21. And that's all I have for the columns. So I think I'm done with the first row and the 3 columns that I have here. So now let's take a look at the second row and the first column. Second row, first column would be my second row. It's 2. First column is 1. 2, 1 slot. It'll be 1 times 4 plus negative 5 times 1. That's negative 1. And then I have a 1 times 3. Negative 5 times negative 2. That's positive 10. 3 plus 10 is 13. And then 6 minus 15 is negative 9. Okay. So there's another interesting development that we should examine here. A is a 2 by 2 matrix. And then B is a 2 by 3. 2 by 3 matrix, right? And notice when we're doing the dot products here, the number of, whenever I swipe my marker, my highlighter in the first matrix, I'm counting the number of columns that I have, right? I'm counting the number of columns that I have. And then whenever I swipe my highlighter on the second matrix, I'm swiping down, and so I'm counting the number of rows I have there. So it turns out that when you're doing matrix multiplication, that these two numbers here, the number of columns for the first matrix has to be equal to the number of rows in the second matrix. Yes. Number of rows in first matrix has to be equal to number of columns in second matrix. Wait, sorry. Number of columns has to be equal to the number in the first matrix. That would have been bad. That's the match. If it doesn't match, you can't do it. Right? Does this match? So BA, we're looking at B, which is a 2 by 3 matrix. We want to multiply that by A, which is a 2 by 2 matrix. This doesn't match. So if we attempt to do this, 4, 3, 6, 1, negative 2, 3. Try to multiply that with 2, 3, 1, negative 5. We see that we're going to run into trouble already when we take a look at the first row and try to dot that with the first column. So there has to be certain rules to these matrices that when you're multiplying the matrices, it has to match. So here, we're unable to do this product, so the product doesn't exist. So already this would be a good justification to say that AB is not equal to BA. In this particular case, BA doesn't even exist. All right? So not only that, when we're taking a look at the one that did work, if the number of columns for the first matrix matches the number of rows for the second matrix, not only can you make it work, but you should also be able to anticipate the dimension of the new matrix. So the new dimension will be a 2 by 3. Yeah?
Is the answer always going to be the higher column?
No, the answer is just going to be the outside. So the first number here is going to be the row. The second number here is going to be the column of your resulting matrix.
So it doesn't matter what?
Doesn't matter
Okay.
as long as these two match up to be the same. Right? Yeah. No. Even if they're the same size, your answers might be different. So even if they're the same size, which means you can do it, your answers might still be different. Yeah. The projection is just one example where you're probably going to get it to be not the same when you switch the order. And there's many more examples instead of, aside from just the regular 2 by 2 matrix. So it's important that So this is the way we kind of did it the second way, which was supposedly easier, and this is how you would write it mathematically, which is not always the best way to do this. But to get the ijth element in the in the product, then you would have to do a dot product between two things. So this is like I said, it's a complicated way of writing it. I think if you just go through the process, then you should be able to just practice doing matrix multiplication. Unless you're a math major, then you have to try to make sense out of this. I think I'm missing one. AI1.
In the slides, it starts out with just a equals plus sign.
Oh, yeah, that's, I copied it from the slides.
A2, B2, J.
1J.
So it's just those
So it's missing the first one. This is the first one.
column row matches.
Yeah, the column row matches. So again, AB, if A is an M,
One you just drew is the next term. They're plus signs.
oh, I don't know. I don't want to think about it right now.
Because the AI2 is like, columns rows 1 through whatever. Row 1 through 2.
Yeah, I don't know if this is good notation. I'm going to look at it again carefully later on. So back to what we were talking about here. Earlier we said that these have to match, these numbers have to match. And not only that, but your new matrix will be the first matrice's number of rows and the second matrix's number of columns. So your new matrix will be an M by P, whatever those are. Okay? As long as the middle one matches. All right. 5 minutes. We got properties for multiplication and warnings for multiplication. So those two pieces of information are important. So it's not commutative, but it turns out that matrix multiplication is associative, provided that they're the right shapes for each other. It's also distributive from the right side and distributive from the left side. It's also associative in a strange way with scalars. So if you have a product of a matrix, you're going to scale or multiply that by R. It's like scaling multiply the first matrix or scaling multiply the second matrix and then doing your multiplication. But you have to remember the multiplication has to be the A's on the left and then the B's on the right. And then it also has a multiplicative identity. And the multiplicative identity is the identity matrix. Now, the identity matrix coming from the left might be different from the identity matrix coming from the right. And so these are identity matrices. These are square identity matrices, but different sizes. Because if you multiply something from the left, it has to match a number of columns. And if you multiply something from the right, then it has to match a number of rows. Wait. If you multiply something from the left, it has to match the number of rows. And if you multiply something from right, it's going to have to match the number of columns. Okay? Now, let's take a look at the warnings. And the warnings are things that we would expect to be true because they work for real numbers, but it turns out that real numbers and matrices are not all the same thing. First of all, multiplication is not commutative, but there are cases, special cases, that they actually do equal to each other. And the example that we had where we stretched the vector and then we rotated it, that's a special case because if we rotate it first and then stretch it, it'll be the same thing. So in those special cases, we can say that those transformations commute. In some other cases, they don't commute. In general, you can't just switch the order of products with matrix multiplication. The cancellation law doesn't hold. You know, we got 2x equals 2y. You cancel the 2's. That was easy back in pre-calculus or algebra. In matrix multiplication, you can't just cancel something out. So if AB equals AC, you can't just get rid of A and say B is equal to C. That's not necessarily true. And also the zero property doesn't hold. We know that if we have two numbers that we're multiplying and it's equal to 0, that means one or the other or both are equal to 0. That's not true for matrix multiplication either. Just because a product of two matrices equal to 0 does not mean that one or both of those matrices are equal to 0. They could be both non-zero matrices, and then when you multiply them, you get 0. Okay. So those are some of the warnings that seem to be true for real numbers, but are not necessarily true for matrices. Okay. We have a couple more topics here, and then we're going to get into the inverse of matrices, which is going to be a challenge for us in the beginning. All right, see you guys next time.
Just one thing